Have you ever stopped to think about the tiny object hidden inside your smartphone? Right now, you're probably holding one in your hand. You use it every day to send messages, watch videos, browse the internet, or navigate your way home. It has a beautiful display, powerful cameras, and a battery that lasts all day. But none of those things would matter without one tiny component hidden deep inside. That tiny component is the semiconductor chip. It's so small that most people never even notice it. Yet it performs billions of calculations every second. It powers your phone, your laptop, your car, your smart TV, and even the satellites orbiting above Earth. Many experts believe semiconductor chips are to the 21st century what oil was to the 20th century. They have become one of the world's most valuable resources. But here's something that surprises almost everyone. Despite all the world's technological advances, not a single country can independently produce the most advanced semiconductor chips from start to finish. Not the United States, not China, not Japan, not South Korea, not Taiwan. How can that be? How can humanity build reusable rockets, artificial intelligence, and space telescopes capable of seeing billions of light years away, yet still depend on dozens of countries to manufacture one tiny chip? The answer is far more fascinating than most people realize. The story begins with one simple question. What exactly is a semiconductor chip? At first glance, it doesn't look impressive. It's just a small black square, usually hidden beneath layers of metal and plastic. Most people will never see one in their entire lives. But inside that tiny package lies one of the greatest engineering achievements in human history. Every chip is built on an ultra-pure piece of silicon, a material made from ordinary sand. It's hard to believe that something as common as sand can become the foundation of artificial intelligence, space exploration, and modern computing. Silicon has one remarkable property. Under the right conditions, it can control the flow of electricity with incredible precision. That single characteristic changed the world forever. Engineers discovered they could create tiny electronic switches called transistors. Each transistor has only two states, on or off. It sounds incredibly simple. But when billions of these tiny switches work together, they become something extraordinary. Every text message you send, every photo you take, every song you stream, every GPS direction you follow, and every AI response you receive all begin as billions of tiny electrical signals moving through microscopic transistors at nearly the speed of light. Today's flagship smartphone processors contain tens of billions of transistors packed into an area smaller than a postage stamp. To appreciate how small they really are, imagine shrinking a football field until it fits on your fingertip. Now imagine building an entire modern city inside that tiny space, complete with roads, intersections, power lines, and traffic systems. That's the level of complexity engineers deal with every single day. And here's where things become even more unbelievable. A human hair is about 80,000 nanometers wide. Many of today's most advanced chips are manufactured using processes measured in just 3 nanometers. At that scale, atoms themselves become engineering challenges. Building structures this small isn't like manufacturing cars or airplanes. It's closer to performing microscopic surgery, billions of times, without making a single mistake. Because even the tiniest imperfection can destroy an entire chip. That's why producing advanced semiconductors is considered one of the most difficult manufacturing processes ever created. And surprisingly, creating the chip itself isn't even the hardest part. The real challenge is building the machines capable of making those chips in the first place. The machines used to manufacture modern chips are unlike anything else on Earth. Imagine trying to draw billions of perfectly identical patterns onto a piece of silicon. Not with a pen, not with a laser pointer, but with a beam of light so precise that even the smallest error could ruin an entire wafer. That is exactly what a lithography machine does. Many engineers describe it as the most complicated machine humanity has ever built. The world's most advanced lithography systems are produced by just one company, ASML, based in the Netherlands. Building one of these machines takes years. Each one contains more than 100,000 individual parts and weighs over 180 tons. The price of a single machine can exceed $300 million. But money isn't the biggest challenge. The real challenge is physics. To create transistors only a few nanometers wide, ordinary light simply isn't good enough. Engineers had to develop an entirely new type of light, known as extreme ultraviolet light, or EUV. Generating EUV light is unbelievably difficult. A tiny droplet of molten tin is fired through a vacuum chamber 50,000 times every second. At exactly the right moment, an extremely powerful laser strikes each droplet, turning it into plasma that becomes hotter than the surface of the sun. Only then can the machine produce the special light needed to print microscopic circuits onto silicon. And that's only one part of the process. The mirrors inside the machine must be so perfectly smooth that, if they were enlarged to the size of Earth, the tallest bump would be less than a few centimeters high. Even a microscopic vibration can throw the entire system out of alignment. That's why these machines operate inside carefully controlled environments where temperature, humidity, and even the movement of the floor are constantly monitored. What's even more fascinating is that ASML doesn't build everything alone. The ultra-precise mirrors come from Germany. The powerful laser systems are developed with technology from the United States. Critical optical components rely on decades of research from companies across Europe and Japan. Thousands of suppliers contribute specialized parts before a single machine is finally assembled in the Netherlands. In other words, even the machine that builds the world's most advanced chips depends on a global network of expertise. This is the first clue to understanding why no country can produce advanced chips entirely on its own. But if the Netherlands builds the machines, who actually designs the chips? And where are those tiny pieces of silicon finally brought to life? If the Netherlands builds the machines, then who designs the chips? The answer takes us across the Atlantic to the United States. Although many people think of companies like Apple, NVIDIA, AMD, Qualcomm, and Intel as chip manufacturers, most of them don't actually manufacture their own advanced chips. Instead, they design them. Think of it like an architect designing a skyscraper. The architect creates every detail of the building, but a different company is responsible for actually constructing it. Chip design works the same way. Engineers spend years creating incredibly detailed blueprints that describe where billions of transistors should be placed. Every connection, every circuit, and every tiny component must be planned with extraordinary precision. But designing a modern chip isn't as simple as drawing a blueprint. It requires some of the most sophisticated software ever created. These programs are known as Electronic Design Automation Tools, or EDA software. Without them, designing today's processors would be practically impossible. And here's another surprising fact. Almost all of the world's most advanced EDA software comes from just 3 American companies: Synopsys, Cadence, and Siemens EDA. Together, they provide the software used by nearly every major chip designer on the planet. That means even companies outside the United States often rely on American software before a single chip is manufactured. Once the design is complete, another challenge appears. Where can these incredibly advanced chips actually be built? Constructing a modern fabrication plant can cost more than $20 billion. But money alone isn't enough. Years of experience, highly trained engineers, and an entire network of specialized suppliers are equally important. For this reason, many of the world's largest technology companies don't build their own factories. Instead, they send their designs to a company that specializes in manufacturing chips for others. That company is Taiwan Semiconductor Manufacturing Company, better known as TSMC. Today, TSMC produces the overwhelming majority of the world's most advanced logic chips. If you own an iPhone, there's a good chance its processor was manufactured by TSMC. Many NVIDIA AI chips, AMD processors, Qualcomm smartphone chips, and even some Intel products are manufactured there as well. It's one of the most extraordinary business models in history. Some of the world's biggest technology companies compete fiercely in the marketplace, yet they all depend on the same manufacturer. This makes Taiwan one of the most strategically important places on Earth, a single island, responsible for producing the tiny components that power much of the modern world. And that's exactly why the global semiconductor supply chain has become one of the most important economic and geopolitical stories of our time. Now imagine standing inside one of TSMC's fabrication plants. At first glance, it doesn't look like a factory. There are no sparks, no loud machines, no workers carrying heavy equipment. Instead, it feels more like a giant scientific laboratory. The air is cleaner than an operating room. Temperature, humidity, and air pressure are controlled every second. The reason is simple. At this scale, A single speck of dust can be larger than an entire circuit on a modern chip. One tiny particle could destroy hundreds of chips worth millions of dollars. The process begins with a perfectly polished silicon wafer. It looks like a shiny circular disc about the size of a dinner plate. Although it seems ordinary, this wafer will eventually contain hundreds of powerful processors. The wafer moves through hundreds of manufacturing steps. A thin layer of material is added. Then another layer is removed. Next, an advanced lithography machine prints microscopic circuit patterns onto the surface. This process repeats hundreds of times. Every new layer must align almost perfectly with the previous one. The margin of error is measured in billionths of a meter. Even the smallest mistake can ruin an entire wafer. After the circuits are complete, powerful inspection systems search for defects too small for the human eye to see. Only the best chips continue to the next stage. The wafer is carefully cut into individual chips. Each chip is placed inside a protective package and connected using advanced packaging technology. Finally, every chip is tested before leaving the factory. Some will power smartphones. Others will become AI processors. Some will control medical equipment. Others will fly aircraft or operate satellites. It's incredible to think that something made from ordinary sand can eventually become the brain of the world's most advanced technology. But the journey still isn't complete. Even TSMC cannot build a modern chip entirely on its own. If building a modern chip requires so many countries working together, one question naturally follows. Why doesn't a single country simply do everything itself? After all, the United States has some of the world's best engineers. China has invested hundreds of billions of dollars into its semiconductor industry. Japan is famous for precision manufacturing. South Korea produces some of the world's most advanced memory chips. So why can't any of them become completely independent? The answer is surprisingly simple. The semiconductor industry didn't grow inside one country. It evolved across the entire world. Over decades, different nations became exceptionally good at different parts of the process. The United States focused on research, chip architecture, software, and innovation. The Netherlands specialized in advanced lithography machines. Japan became a global leader in ultra-pure materials, silicon wafers, specialty chemicals, and precision manufacturing equipment. Taiwan perfected large-scale chip manufacturing. South Korea dominated memory chips and advanced semiconductor production. Malaysia, Vietnam, and the Philippines became important centers for assembly, packaging, and testing. Each country invested billions of dollars, developing expertise that took decades to build. Trying to recreate all of that inside one nation would be incredibly expensive. More importantly, it would take many years. Money alone cannot replace decades of experience. That's why even the world's largest technology companies continue working together instead of trying to do everything themselves. The semiconductor industry isn't just about technology. It's about cooperation. And that's exactly what makes it both incredibly powerful and incredibly fragile. This interdependence also explains why semiconductors have become one of the world's most important strategic industries. In recent years, the competition between the United States and China has brought the chip industry into the global spotlight. At first, many people assumed it was simply a trade dispute. In reality, it goes much deeper. Whoever leads semiconductor technology will have a major advantage in artificial intelligence, advanced computing, telecommunications, defense systems, and future industries that have not even been invented yet. Because of this, governments around the world have begun investing heavily in domestic chip production. The United States introduced the Chips and Science Act to strengthen manufacturing at home. The European Union launched its own Chips Act to expand semiconductor production across Europe. Japan increased support for new fabrication plants and strategic partnerships. China has invested hundreds of billions of dollars to reduce its dependence on foreign technology. These investments are not just about business. They are about national security and long-term economic stability. However, building a competitive semiconductor industry is not something that can be achieved overnight. Constructing a fabrication plant may take several years. Training thousands of highly skilled engineers can take even longer. Developing an entire network of suppliers often requires decades. This is why the global semiconductor industry cannot be reshaped overnight, no matter how much money is invested. Even today, companies and countries still rely on one another in countless ways. The reality is that no single nation possesses every technology, every supplier, every material, and every manufacturing capability needed to produce the world's most advanced chips completely on its own. The semiconductor industry has become a perfect example of how innovation grows through global collaboration. It is also a reminder that in today's connected world, technological leadership is rarely achieved alone. So, the next time you pick up your smartphone, take a moment to think about what you're really holding. Inside that small device is far more than a powerful processor. It's the result of decades of scientific discovery, engineering breakthroughs, and international collaboration. The silicon may have started as ordinary sand. The chip could have been designed in the United States. The manufacturing equipment may have come from the Netherlands. The ultra-pure materials could have been produced in Japan. The processor itself may have been fabricated in Taiwan or South Korea. It might have been packaged and tested in Malaysia, Vietnam, or the Philippines before finally reaching the factory, where your phone was assembled. By the time it reaches your hand, that tiny chip has already traveled thousands of miles and passed through the expertise of countless engineers, scientists, and technicians around the world. That's why a semiconductor chip is much more than a piece of technology. It represents one of humanity's greatest examples of global cooperation. Every breakthrough depends on knowledge shared across generations. Every new generation of chips pushes the limits of physics, chemistry, materials, science, software engineering, and manufacturing. And despite growing competition between nations, one fact remains unchanged. No country can truly stand alone in the world of advanced semiconductors. The smartphone in your pocket is proof of that. It reminds us that some of the world's greatest achievements are not built by one company or one nation. They are built by people working together across continents, each contributing a small but essential piece of a much larger puzzle. As artificial intelligence, robotics, quantum computing, and autonomous vehicles continue to evolve, semiconductor chips will become even more important than they are today. The race to build faster, smaller, and more efficient chips will continue. New technologies will emerge, new factories will be built, new companies will rise, but one thing is almost certain. The future of semiconductors will continue to depend on global collaboration because the world's most advanced technology has never been the work of one country alone. And perhaps that's the most remarkable story hidden inside the smartphone you use every single day.